So, welcome. I'm glad you could make it. It's good to be here. I'm going to be your tour guide as we go through some concepts in deep learning. We'll do some TensorFlow and then a little bit of Keras. And there's a few things that are going to come up along the way, which I'll let you know when we get to them. So, just with a show of hands, how many people are new to deep learning? Oh, yeah, you're in the right place. And I'm going to, can you hear me in the back? So. Okay. Is that better? Okay, good. My DJ voice. And so I'm going to put the slides up on SlideShare. And some of them I'm not going to go over because they're not really quite that important for tonight, given the time constraint. So I'll try to hit the highlights. And we'll look at what a neural network is, deep neural network, and then we're going to look at linear regression, and then we're going to go to a CNN, convolutional neural network, then a little Keras, then a little bit of TensorFlow, and then some of the fun stuff, and then you'll get the reward prize at the end. So with that in mind, has anyone attended any of my other presentations? Only one? Okay, good. So everybody else still, just pretend you didn't hear my same lame jokes from last time. Okay, I've got a kind of a summary here, and I've color-coded it. Doesn't quite come out that well, but with the concepts for neural networks, for deep learning, they're kind of in clusters. And so with hidden layers, initialization, neurons per layer, they kind of go together. And then there's the next three, and so on and so forth. So those things that are colored are hyperparameters, and those are the things that you tune. So you set the values before you start the trading process. And the way to do that is, well, it's kind of trial and error. There are tools out there online that you can use that'll do the hyperparameter tuning for you. There's a rules of thumb, there's this and that and the other. It's an imperfect science. So it's kind of art, science, swag type stuff. So I'm going to start with this slide because it's a little bit out of date, and let's see, but it's got some, we're going to look at parts of the red dot. So there's data mining, data science, big data. Now, data science does kind of overlap with deep learning because you can use Keras and TensorFlow in R and RStudio, so it's, it should be updated a little bit. There's another thing that's not there, it's called reinforcement learning. That's actually part of machine learning. It's separate from deep learning, but when you take the combination, it's called deep reinforcement learning. That's going to be big. It's gaining momentum in a lot of different ways. Could be some big breakthroughs this year in algorithms. That's what people are hoping, thinking, wishing, and so forth. So the thing with the three circles over there gives you a kind of an idea of the relationship. There's artificial intelligence, and then the smaller one is machine learning, and then there's deep learning. In simplified terms, AI, artificial intelligence, you can think of it, if you were to summarize it just to pick one word, it would be rules. You have a bunch of rules and some conditional logic and a little bit of data. And they can become very complex very fast and cumbersome and difficult. And yet, people were able to create expert systems in the 80s, which are very powerful, and they're still around. Meanwhile, machine learning and deep learning is based on lots of data, lots of computing power, new algorithms, improved algorithms. So you don't quantify, there's no if, else if kind of stuff. You just provide the data, and then the framework that you're going to probably be using, whether or not it's Keras, TensorFlow, PyTorch, does all of the calculations. And there are lots of them. You will be very happy when you see some of the stuff I'll show you that you don't have to do it by hand. So just another thing, the term AI was first used in 1956. At the beginning of the summer, there was a conference at Dartmouth, and John McCarthy is the person who came up with that term. So 63 years ago, I'll show you that slide later. So it's still fairly, it's 20th century, not too old. And so that was all planned, to distract you. And so You know, I say use cases for deep learning. I'm not going to go into historical stuff, the marketing related stuff, because the answer pretty much is when, if, what. It's usually everything. So, you know, here I have many others. Most of the stuff that we do, sooner or later, it's going to be, somebody's going to do something with it with deep learning, or at least machine learning. So this is the one that's kind of a little strange when you first see it. How many have seen this before? Okay, so the people who are new are the ones who haven't, obviously. So it looks kind of like this cold mess of stuff. And I'll just give you the really condensed description of the goal, the target, and then I'll come back with the details. The idea is that we want to have a data set. It could be a CSV file, text file, Excel spreadsheet, doesn't matter. They're numeric values. You got to make sure that's the case. Take each row, feed it in from the left side. That's the input layer. And there'll be some numbers in there, and they'll be represented, there'll be matrices. So you'll multiply them, you go across, that's forward propagation. And then the network, or the framework that you're using, will do the heavy lifting. And it's going to compute some numbers to update those weights. And it'll adjust, so it'll go all the way back. It's called backward error propagation, or backprop. And you do that with each row in the data set. And then that's called an epoch, E-P-O-C-H. And you might do that multiple times. It kind of depends. And at the end of that process, you'll have a trained neural network or a trained model, same. And then you try to figure out, is it well trained or not? And there's some stuff you can do with that. So the training part takes place, the training the model takes place with training data, usually 70% of the data set. Then after you've done that, you lock down the model, you look at the test data, and you just do forward propagation. That's the inferencing. That's the predicting. And you compare the two numbers. And then if they're the same, close, then you probably got to train it well. If not, then you've got some other things to deal with, which we'll get to. So coming back to the beginning, I mentioned the input layer, there's the output layer, and then the stuff in the middle, these hidden layers. It might sound like some weird voodoo logic stuff going on. It's not. It's just intermediate computational layers. How many are there? That's up to you. It's a hyperparameter. How many neurons in each one? Another hyperparameter. What about initializing the weights? Hyperparameter. And there's several ways of doing it. One is to take random numbers between 0 and 1. It could be a normal distribution or whatever. Let's just pretend that that's all been done. So it's populated with numbers. Those are the initial weights. And so we take a row of data as a vector, multiplied by between two consecutive layers, adjacent layers is represented by a matrix of weights. So you multiply, you keep getting a vector all the way to the end. Now, I'm going to flip back and forth a little bit because there isn't any one picture that captures everything nicely, conveniently. This neural network versus this one. Forget about the fact that there's a different number of nodes. That's irrelevant. What do you see on the right end? The output layer? There's only one output node. This is going to be what you would use for linear regression. This is a classifier because there are 4. Nothing special about 4, but that means you're probably going to be doing something like checking, is it a bird, cat, dog, fish, for example. You're classifying stuff. That would be like an image. There's an MNIST data set which has hand-drawn digits, 0 through 9, so there'd be 10 of them out there. And what happens is at the end, think of it as like last layer is like a buckets. They'll be populated with numbers that are between 0 and 1, and the sum of that whole row, column rather, is 1. So it's a set of probabilities. And then you pick the spot, the bucket, the index that has the largest number, and then you go back and go, does that correspond to what was entered in, what was supplied? And if it's the same, it's a match. Now here's the thing. This is a key point. Those numbers there, there's never going to be a 1, because every number is bigger than 0, so none of them can be 1. So you just go for the biggest number that's there, but then over here, that input, if it's a digit, you have this thing called one-hot encoding. And what that means is where there's that digit that you're looking at, let's say it's a 3, there will be a digit 1 in this 1 by 10 vector. The rest will be 0 because it's a 1 with probability 100%. And so for the first position, it would be a 0, there'll be a 1. So what you do is see, since it's a 1 in the 1 hot encoding and it's never 1 over there, how do you compare them? You look at the index. Look at the index of the largest number on the right, and look at the index where the 1 occurs in the 1 hot encoding. And that's how you make the comparison, if the indexes are the same. It's a tiny little point, but it's important because without that, it's guaranteed to fail. So now, the next thing, I'm going to work with this one here, a little bit more so, because I'm going to show you a data set where I mentioned you pass in each row. Now, this is the Titanic data set, or it's part of it. So you have a lot of these attributes. Some of them are more important than others. The point of this, what you want to try to do, you see this column here, survived? That's the thing that you want to predict, to determine. So 0 didn't survive, 1 did survive. Now, the numbers could be completely different. It's just, in this particular case, that's the choice of the target variable. It's going to be a 0 or 1. So I mentioned this because the input, remember I said you input every row? You input each row except for that column. And you input that, and then you pass it along, and it gets through to the end, and then you compare what this thing calculates with the actual correct value in that spreadsheet. And you take the difference. Now, of course, the numbers were random at the beginning, so it's not going to be correct. So the difference is called the loss or the cost. And what you want to do is minimize the cost. So each time you go through with another row, have that difference decrease as much as possible. And so this is the heavy lifting part on that side. The framework then allows you to choose something called a cost function, hyperparameter. And so the idea of reducing the cost, let's imagine we're on a hill, we're skiing. How do we get down to the bottom of the hill as fast as possible? Well, if there's a straight line, of course, we would take that. But generally, are there any skiers in the room? Okay, so generally you go like this, right? You zigzag your way down, and at each point when you're going down, you try to maximize your descent. That's what gradient descent is about. You're always trying to maximize that. Now, for the most part. So the cost function there is based on those weights, those edges and the weights and so forth. So it's aware of all of that stuff. So the thing is that there's different types of ways to go down, just like you have different types of skis. You go faster in some ways, and depending on the terrain. Well, in our case, it's not they're called optimizers. There's about 6 or 8 of them. And so that's another hyperparameter. Then there's a number called the learning rate. It's between 0 and 1. Very important number, because it affects the rate at which we get to the bottom. So by analogy, if the number is too big, when we go down, we end up going past the minimum, and then we just kind of fly off into nowhere. If it's too small, it takes too long. There's another scenario where we could actually oscillate back and forth. But the idea is to get the right number so we just come to a nice soft landing, so to speak, like an airplane landing in an airport. So those 3 things go together: the cost function, the optimizer, and the learning rate. They'll always be there when you're doing backward error propagation. So now, what do? We got those 3 on to initialize, we got the 3 on that side. So let's take the MNIST data set. So it's going to be like this in this case, with 10 items on the output layer. So that set has 55,000 rows, and one epoch is 55,000. So if we do it 20 times, what does that mean? It means 1.1 million times of going forward and back, always updating constantly. And at the end, you add up and figure out the percentage of the things you got correct. So let's say it's 90%. What does that mean? Is it good? Is it bad? Is it average? Well, this is where the testing part comes in. We do the same thing, but just forward propagation, calculate the percentage. If it's statistically more or less the same, then it was probably trained well, and then you maybe want to tweak it, get a little bit of extra accuracy out of it. If it's not, then you probably have something called overfitting. And if you haven't heard of that, by analogy, I would say, think of signal and noise. And if you have too much of the signal statistically counted as though too much of the noise counted as signal, that's kind of like overfitting. So we want to get rid of the noise, stop treating it as though it were signal. And one technique for that is called a dropout rate, which is very interesting. It's a number between 0 and 1, and it's treated as a percentage. So 0.2 means 20%. And when you define the model at the beginning, you specify that number. And what happens is, every time you do the forward propagation, the framework that does the calculations will ignore that 20% randomly selected. And then the next row you pass in another 20% randomly selected. And it actually works, believe it or not. And so some of the values that you're going to have could be 10%, 0.1, 0.2, 0.3, 0.4, even 0.5. That's 50%. Seems like a lot. It would be for the other one, it'd be overkill. But if you have 100 million edges and you ignore 50%, you still got 50 million of them. So it actually really does work. By the way, I call it the ginkgo biloba of deep learning because if you've ever taken that stuff, it thins your blood. So, you feel more energetic, lighter, and all that other great stuff. And, it improves your memory too. So we got that kind of counterpart. And this was the person who came up with this, Geoffrey Hinton. They call him the godfather of deep learning. So how many hyperparameters we talked about? The 3 at the beginning, the 3 over there, then this one here. There's one more. And this one's really important. And I don't know if you noticed it. It's the one that, well, you see, this neural network that I described to you, this thing is linear. And by analogy, suppose you want to multiply the first 5 numbers together. Now typically, which is 120. Typically what you do is you have that 120. You don't use the intermediate calculations. You don't calculate that number every time. Matrices are products and sums. And if you have a set of matrices and you multiply them, you don't have to multiply them individually every time. You can just multiply them together and get one matrix, which then collapses this into an input matrix and output, which defeats the purpose of the hidden layers, which are where the computations take place to help us come up with this trained model. So we need to make it nonlinear, and that is done with an activation function. And there are lots of them. Sigmoid, tanh, ReLU, rectified linear unit, and then there's various variations of that as well. So used to be popular with sigmoid and tanh. Now they use ReLU. It's the simplest one, ironically. But the first 2 are actually used in something called RNNs. It's out of the scope of tonight. Recurrent neural networks. So there's one type called LSTMs, long short-term memory. And so they have these input gates and stuff, and they use sigmoid and tanh. Still very, very useful. They solve certain problems that can arise when you're dealing with these kinds of networks. So anyway, one thing I wanted to point out, which I didn't see, when I said we input the row and then we ignore the number and do all the calculations, why the heck are we doing this if we already know the answer? Going through all this trouble, training and so on and so forth. It's so that we can create see, this thing there's no prediction in this spreadsheet. It's just a bunch of numbers. We want to get a trained model so that we can then predict things. So where we don't have the answer, that's the point. Otherwise, we're just wasting our time. So now, if you are thinking about classification, where you've got the cat, dog, bird, fish, and so forth, you say, well, why would I need a neural network to do that? I can just eyeball it and figure out what's what, right? Isn't that right? I mean, we can all do that. Well, in that case, how many of these do you think you can classify correctly in, say, 15 seconds? I have to look every time, multiple times, because I think it kind of, eyes going back and forth, glazing over, and kind of sort of more or less, But, so, a neural network can be trained to identify this very accurately. It can work 24 hours a day, never stop, and always outperform humans as well. So that's one of the rationales, at least for classifying images. Now I mentioned this sigmoid function. It's based on a number called Euler's constant. Anyone familiar with that? It's 2.718, etc. It looks like this. And it's got some interesting properties. For example, for derivatives, if you look at the function y equals x squared in the plane, what's the derivative? It's 2x. And x cubed, 3x squared. And if y equals sine x, the derivative is cosine. If y equals cosine, negative sine, etc. The derivative of y equals e to the x is e to the x. Interesting property. It's the only non-zero differentiable function in the plane that equals its own derivative. And so with that, here we have the sigmoid function. And this, it lies between 0 and 1. So any set of numbers that you supply will return a set of numbers between 0 and 1. So you'll get a nice set of, it's called squashing, because neural networks like smaller numbers. And if you don't like that form, you can multiply by e to the x, top and bottom, and then you'll get e to the x on the top, and then e to the x plus 1 on the bottom. So they're both positive, and the bottom's a little bit bigger than the top. So it's always going to be between 0 and 1. So, just as a side segue thing, the graph didn't come out too nicely, but so regardless of how big a number you provide, positive, how large negative, the result is a number between 0 and 1. Conversely, given a number between 0 and 1, I'll just go across horizontally until I hit it on wherever I cross that curve. And I'll get a number that's outside that range. So what does that tell you? Well, the cardinality of the real number line is infinite. It's uncountably infinite. And the cardinality of that interval 0, 1 is the same. Kind of counterintuitive, you would say. And it's actually true for any interval, no matter how small. Take 0, comma epsilon. Let's make it really small. Let's say epsilon is 10 to the negative 1 quadrillion. Nothing on Earth could measure what's in there. That interval has the same cardinality as the real number line. I think that's kind of amazing. So you can have fun with numbers too, if you really want to. So here's tan h. Notice it's very similar. It has the same e to the x, e to the negative 2x. So this is the range from negative 1 to 1. And this is ReLU, which is very simple. The ReLU of x is maximum of 0, comma x. So it's 0 when x is negative, and then it's equal to x when it's bigger than or equal to 0. So those other functions that you saw, they're all differentiable. They're all smooth. This one is differentiable except for 0, where it's continuous, because it's got a little kink in there. And they're all monotonically non-decreasing, which means when you go from left to right, they stay the same or they increase. They never drop down. That's a common property that you'll see in these things. And then there's this one, which, you know, that last layer I told you about with the 10 buckets and all that? Before that, there's a layer, and that layer is connected with everything in the previous layer is going to be connected with all those 10 outputs. And it's going to use this thing called the softmax activation function. If you get rid of the e's, you're just getting proportional values, like z1 over the sum z1 to zn, then z2 over the sum. Well, you make those exponents, then everything here is non-negative. The denominator is never 0. And you'll get a set of numbers between 0 and 1, and the sum equals 1. So it's very handy for that particular case. So here are the equations, or the formulas in Python. Notice, sigmoid, it kind of looks like what we were just looking at. Tan h is actually called tan h. And then for ReLU, it's the maximum. This is the vectorized form, not the scalar. So W is a matrix, and X is a vector. So it does a component by component. Same thing to all of them. And so I mentioned this already about what was popular. And so now let's go to linear regression. Technique that was developed in 1805, 214 years ago. Carl Gauss, the famous Carl Gauss. And so as you can see, the equation of a line in the plane is y equals mx plus b. M is the slope, b is the y-intercept. That describes all lines in the plane except one type. And there's an infinite number of them. Vertical lines, like x equals a constant. But that can be represented by ax plus by plus c equals 0. We're not going to worry about vertical lines. Forget about that. We're just going to use this. So Which of these data sets look like they could be represented nicely, accurately by a line? The one in the upper left, yeah. Lower right, sure. The one in the upper right looks kind of quadratic, parabolic. The one down below, there's the vertical line, see. So the data depends, the accuracy of your model depends a lot on your data. And so how do we figure out how to get this best fitting line? The key idea is to calculate the residual. And that means, I don't know if you can see them, but there's 1, 2, 3, 4, 5 dots, and then the green thing, and then that caret 2. What you do is you take the difference and you square it. And then you take the sum. So you take the sum of the squares of the difference of the vertical values of the point and what the y value would be of that point if it was on that best fitting line, and divide by the number of points. That's the cost function. And that's one of the reasons why I'm showing you this. So let's take a look at this. Unfortunately, you can't really see this well, but the residual here, over there, it's 1 squared, negative 1 squared, negative 1 squared, 1 squared, 4. In this one, you got 2 squared plus negative 2 squared. That's 8. There's 10 points in both of them. The first one, it's going to be the mean squared error, 4 over 10. This one's 8 over 10. The other one's a better fitting line. Not necessarily the best, but it's better than this one. So having a best fitting line is not necessarily related to the number of points that you intersect. Those are kind of overlapping concepts, but they're scenarios, but they're actually distinct. So, because you'll hear a lot of people say, it's just curve fitting. Not quite. So we extend this idea. This is the key idea, doing this. So what's going to change? The number of points. So here, like that. And keep in mind that, well, when you look at this, it kind of looks like the right line. It's the best fitting, sort of. If you take m and you change the value of m, you're just going to rotate the line. If you change the value of b, it's a vertical translation. So you can kind of sort of eyeball it and go, yeah, it's probably the one. How do we quantify that? By taking that sum that I told you, the sum of the squares, it's quadratic, so it's not elliptic, it's not hyperbolic, it's a parabolic shape, and it kind of looks like this as the cost function. And this is called a convex surface. So it can only have a maximum or a minimum. In this case, obviously a minimum. That's the point that we want for the best fitting line. And when we get that point, the value of m and b at that point is exactly the right value that gives us the best fitting line. So we're done. If only everything else were that simple. This is the simplest case that you can come across, pretty much. So let's take an example of what we would do with linear regression. If we were to predict the cost of a house, the vertical axis and the horizontal axis is the number of square feet, not a very accurate model. In fact, probably a very poor model. Something like this would be better. We have a lot more attributes, a lot more features. In fact, there's some data sets out there that have more than 30 features related to the cost of a house. Things like the crime rate in the nearest zip code, the distance of the schools, hospitals, all that kind of stuff. So it can get pretty complicated. And so the equation starts looking like this. Still linear, it's called a hyperplane. And so instead of y equals mx plus b, you have w1 x1 plus w2 x2 all the way to the end plus b. And then this is going to be the equation to represent the values for those features for a particular role. Okay, so just to kind of go back to the cost functions I mentioned, this one here, we looked at that. Here's another one. This one's problematic at the origin because in one direction it's a minimum, in the other direction it's a maximum. This is called a saddle point. It gets a little stranger as well. This is a cross-entropy function, and just to give you a very high-level, unfortunately vague description, I guess, the cross-entropy is a measure of the extent to which two probability distributions differ. And why does that matter? Well, because the data has a probability distribution. You don't know what it is. Then you've got the one that you've calculated, kind of, sort of, and then you try to compare them based on that. So if the entropy is 0, well, then you got it perfect. And it's never going to be that, but how close it is, how far it is, the number, and it involves logarithms and stuff. But that's the rationale. And so it started from the original entropy thing, and then that became cross entropy, and then there's the Kullback-Leibler divergence stuff, and then there's other ones, and they get really hairy. But it's still based on the idea of entropy initially. So these are some of the, switching gears again, some of the optimizers I mentioned. SGD, stochastic gradient descent, that's the kind of granddaddy. The other ones are variations of it. They all have advantages and disadvantages. And so here's the summary, pretty much of everything we've said so far. And so I just want to give you a very brief sort of one-slide summary. I mentioned CNNs and RNNs. So as of 2 years ago, approximately 60% of neural networks are CNNs, which we're going to look at in a minute. And then there's the rest of them. The thing is, what's interesting, I think, when I showed you that first neural network, by the way, deep neural network means it has at least 2 hidden layers. That's it. Very deep neural network means it has at least 10. That's actually the definition. So the first layer, remember the input I said was numbers. So if we have data from housing, from the Titanic, and if it's not, you have to convert it. Can you do anything? Is there any other type of data set that you could use? For example, what about audio? Well, audio is a number, right? There's a frequency. And if you go onto Wikipedia and you look at audio, the way it's encoded, there's like 12 different parameters. It's really interesting. Some of them don't make any sense at all to me, but they're available. So you could actually use a set of audio signals, convert them to numeric values, and then you have your input vector. The neural network doesn't know where the numbers come from. What about words in a sentence? Well, it turns out that you can actually come up with ways to map words in a sentence to numbers. And then you get a sentence, you can represent it by a vector of numbers, and voila, you can put that in as well. And in fact, that's how it works. When you look at NLP, and with deep learning, and then with the deep reinforcement learning and so forth, it puts all this stuff, really amazing stuff is done. So now, CNNs, convolutional neural networks. This is going to be a little bit weird in parts. And the idea of this is, it goes in, I'll show you the basic one. There's 3 things that you do, and then you do it again, and then you do the last layer. Apparently our eyes are designed whereby parts of them can recognize vertical things, segments, lines. Other parts recognize horizontal or at an angle. That's sort of the kind of the impetus, the idea behind it, and here's the leap. What happens is, with the neural network, in the framework, what you do is you request programmatically these filters, and they're 3x3 arrays of numbers, and generally, 8, 16, something like that. And so you can't see it very well, but each image is a set of numbers. They're pixels, 0 to 255. And so you scan across. I can't do this very well here, but you start from the upper left, take the 3x3 filter, and multiply correspondingly with the 3x3 in the image. So you have 9 products and 8 sums, and you get the result. You put it over there, and you move across. 1 column at a time, default. You populate some numbers, and then you go to the next row. By default, you go down 1 row. And so you scan across, you get some numbers, and that's called a feature map. And it's going to be a little bit smaller, so what you can do if you want is pad it a little bit in the beginning with zeros. So after you do that, it's going to be the same as the original. It's another option. So the next thing you do is apply ReLU. So anything negative, 0. And then the next thing you do, this will seem strange, it's called max pooling, and you subdivide it. We've got a small example of it here. Pretend that's that image, the pixel thing of the image, the 28 by 28. You subdivide it, and you can't see it, but this is going to be 4 numbers, and then another 4, and another 4, and then, sorry, I got ahead of myself. the convolutional calculation with the filters. So there's the filter over here. It's kind of in the middle. That means it's gone across multiple times. It finally reaches that point. So here there's a 1, and this is it's doing this one right here, this 3 by 3. So the 42 and the 1, that gives you 42. That's what you get. All the rest is 0. And that's not a typical filter, but just to give you an idea of how the calculations work. Now, these are filters. You want to sharpen it. These are in Photoshop. GIMP, those other tools, they use these things. This is blur. You're taking the average. And one thing you might notice, as you see, look at the diagonal values and the off-diagonal values. They kind of, sort of, are similar, usually. Here's one for edge detect. You see the ones above, the ones below. That's kind of how they sort of look. And then down below, usually they add up to either 0 or 1. It's a minor detail. And so this is one type of edge detect. There's other ways of doing it too. And so the framework, when you say, I want 16 3 by 3 filters, it gives you the numbers. You don't have to worry about what they are. They're all calculated. And then each one of those filters you pass across the image, create a feature map. So if you've got 16 filters, 16 feature maps, then you do the ReLU, as I mentioned. Negatives replaced by 0. And then, now we get to the, see here, the 4 here, the biggest is 6. The biggest one over there is 8. And then 3 and 4. So whenever I see this, I think of dominant and recessive genes. You're kind of like pulling out what's the dominant part of this set of numbers. And so it's 4 by 4, 16, 2 by 2, 4. You throw away 75% of the numbers. How could it possibly work? Well, by analogy, when you look at compression algorithms, there's lossy and there's lossless. What's JPEG? It's lossy, but it still works. So that's kind of the idea. Now, put a big asterisk next to this because Geoffrey Hinton, the Godfather, said, and I'm paraphrasing as best I can, the tremendous success of max pooling with CNNs has been a disaster. And the reason is that you're throwing away information that could be used for the whole and the part. That's kind of the high-level description. So last year he came out with some stuff. The algorithm that he came up with and other people, it's more complicated, it's harder to train, this and that, but there are some advantages that come up. In fact, it helps with something called GANs. Has anyone heard of those? Generative adversarial networks. Here's an example. We got a panda on the left, this weird thing in the middle, and then there's a panda on the right. The thing on the right is the superposition of the two images, the left and the center. Note, I don't know if you can see it, but here it says it's a panda, 57.7% confidence, and that's a given, 99.3. What the heck happened? That's what an adversarial neural network does. You can find a way to tweak those pixel values in such a way that you can consistently defeat any neural network. And it gets worse. About a year and 4 months ago, somebody on Archive had a paper, came up with an algorithm to do this kind of subversive stuff by modifying 1 pixel. And it gets worse. About a year and a half ago, somebody figured out a way to do this with audio. So who knows what the original is? It can be corrupted. So let's review. We have fake news. We have fake images. We have fake voices. And after that, let's not go there tonight, but it's something to think about. So anyway, here we have, and the next thing is kind of the summary of what I just said. And in fact, if you want to, you can go onto GitHub and get some code and do it yourself, if you feel like it, if that's something you enjoy. So the capsule networks that I mentioned before, they help to be, they're less susceptible to GANs than normal regular ones. So I'm going to go back, since I've got off on that segue, back here. So remember I said the 3? Then what you do, this is for the standard vanilla one, you do the 3, you do it again. And then you take all of those little image maps, and you put them all together into one long vector, and you connect it all to all of the 10 outputs, because I'm talking about the MNIST now. In this case, it would be the 4, but MNIST is a nice standard example. And so then you get these probabilities, and then you look at the slot where you get the biggest value, the bucket, and then the one hot encoded vector, the 1 by 10 vector for the image, and if they're equal, then you get success. So what's that number likely to be? It can't be 1. It can be 0.9, 0.8, 0.7, 0.6. It can be 0.5. The others can't be 0.5 because the sum is 1. It could even be 0.4, 40%. That's pretty low. But you know what? Close enough. And that's what's amazing with neural networks. You can do, this is close, that's sort of close, maybe sort of good enough. Remember we're talking about minimizing the cost function? You don't have to minimize it. You might find another local minimum somewhere. Like, well, I could go for that. You know what? Close enough. That's good enough. You make the decision about what the definition of the success criteria are. It's not done programmatically. So there's a lot of leeway involved here if you want to. And yet this stuff really works, given all of this kind of loosey-goosey flexibility kind of thing. And by the way, here's an interesting thing. The 3 that I mentioned, and then the next 3, and then if you take 2, they're called FC, fully connected. You do that, put 2 of those layers in there. That's called Linnet, capital L-E, capital N-E-T. 20 years ago, that's what was used to figure out the numbers that you wrote when you write your checks, the numeric. That's it. I'm amazed. And they're doing that 20 years ago. I'm sure they added some other stuff to make it more robust, but now you know how it works. It's that simple. There are also other networks out there that have more than 1,000 layers. You know, I got 50 people working at Microsoft. I had 50, 100 people working on it with months. You know, how do you test? You know, when you're adding things, do this, do that, who knows? They figured it out and they got done some really, really amazing things. But this is where it starts from, is this kind of thing. So, now we've done that. And so I want to ask you this. How many people have worked with Keras? Okay, so for everybody else, how much Keras do you think you can learn in 30 seconds? Do you think you can define a convolutional neural network in Keras? Let's find out. And you can start timing it right now. So what do we have here? We got model, of course, sequential. This is a container, basically. Then what do we have? Dense, yeah, that's fully connected. Dropout, yep. Activation, we talked about that. Conv2D, that's the filter. Then max pooling, yep. And then what's next? Eta delta, that's the optimizer. So here, input shape says it's going to be 3 channels, 3 colors, and they're 32 by 32 images. And then the NB classes is the number of classes, 10. So this is MNIST. So model, we instantiate it as a container. Then look, we do add, conv2d, 32 filters, 3 by 3 padding is the same. That's the zeros, you know, to make it the same size output. And input shape is that. The next layer, activation, ReLU. Next, conv2d, 32 3 by 3 filters. It knows from the preceding layer, it's all assumed. You don't have to worry about it. It infers the sizes. And then activation, ReLU. Then max pooling. Then dropout. That's it. I calculated 27 seconds, so close enough. But you now know how to define a convolutional neural network in Keras. That's it. There's, of course, the training part, which we haven't done, and involves the data and so forth. But this is how they start. This is how they work in Keras. Keras is very nice. Keras compared to TensorFlow, kind of a big difference. It's a layer on top of TensorFlow, but see, what the analogy I make is that TensorFlow is like driving a stick shift, for those of you who remember what those are, and Keras is like driving an automatic. And so productivity-wise, development-wise, you can go a lot faster with Keras. If you want to get closer to the metal, you would use something like, you could use TensorFlow, it could be more performant, you know, in the cloud and all this other stuff. And then there's also PyTorch, which is a Python-based rewrite of Torch over at Facebook. And Torch was Lua-based, actually, and it was used by DeepMind. I think it was DeepMind, somebody, whatever. So Now that you've seen that, TensorFlow, a couple of important points. First, don't look at the code too closely because it's 1.x, and when 2 comes out, sometime this year, maybe the middle, all of this will become legacy code. And the main difference is that the new code, TensorFlow 2, is eager execution mode. This is deferred execution mode, which means what you do is you define a graph, and then it kind of does stuff. You define variables and equations, and then you supply data, and it gets kind of cumbersome. So just advance a little bit here. So this is some of this. It supports a number of languages, and it's got APIs. Forget about all of them except Python. That's really it. They're not going to say that, but it's obvious from what they provide, the kind of APIs they provide. It's always 99% of the time is Python. So TensorBoard is a visualization tool. You can see what's in the graph. You can see the accuracy going up, the error rate going down, a bunch of stuff. In fact, TensorBoard is so good, that's what PyTorch uses. Yeah, they use TensorBoard, so it is really good. And I'll show you a very trivial example in a minute. And so here's how you install it. Pip install TensorFlow, voila. And then with that, you got TensorBoard. You're done. And so the use cases, as usual, we know pretty much everything. And then, so we have a graph I mentioned, and then we have edges and tensors. Okay, so the idea is this. There are 3 kind of primitives, if you will. One is constants. We know what those are. Another one is variables. We know what those are. The third is something called a placeholder. A placeholder is like a buffer. Now, you remember in the graph that or the neural network at the beginning, I was saying we input 1 row at a time. You might want to input more. You may want to do all of them. Not recommended, but you can. So you put them in batches. Typically a number that's about power of 2, so 64, 128, but it could be 50 or 100, doesn't matter. So what happens is those batches of data go into the buffer, into the placeholders, and then they're processed. The things that you want to keep, that you're tweaking, that you're tuning, those are going to be variables. There's no other way of doing it. That's how it works. So when you got y equals mx plus b, m and b are the 2 things you want to get the right values for. Those are variables. The y and the x are going to be populated with data values. It's transient. So that's one thing to straighten out. There's other nuances, but again, it's going away, so don't worry about that part. And so what happens is, in order to make this execute, you need to get a session, which is an instance of TensorFlow.session. And usually they call it ses. They don't even want to type it all out. So you go ses equals tf.session, and then there's a run method. So you go ses.run, and you put your variables, whatever, in there, and it executes. So I know what's going to happen. Just hold your breath for a few minutes. We'll get past this. So that's what I just said here, and I'll show you the eager execution in a minute. And so there we go. They're like, you can think of the tensors are like n-dimensional NumPy arrays on steroids. You got a lot of stuff going on underneath and shielded from us, so we don't have to do the calculations ourselves. And so there's some properties here that I mentioned. That's the stuff that, don't worry about this too much. And variable is a class because of the capital. That's what that signifies. And so here's an example. We import TensorFlow as TF. That's the standard idiom. TF.constant 3.0. We print it. We get metadata. We don't get the value. Here's the part where I said ses equals tf.session, print ses.run, a constant, then we get the value. Here, and then you have to close the session. Are you falling in love with this stuff? No. I'll make it a little simpler. Here's what we can do. We can save one line. We can do with. Big deal. We save one line. Here's another example. These are arithmetic calculations. These are actually kind of good. Add, subtract, multiply, divide, and that's what they're called, or div. And so when you print, you get the expected values from that. And so here's some more stuff. Notice that here we have C is a product of A and B. We don't have the values assigned to A and B. This is where the part of the deferred execution happens. So when you're in the session here, down below, I don't know if you can see it, ses.run, C, comma, And then you have this feed dictionary that specifies the values for A and B that are needed to calculate the product, which we know is 6. That's how it works with 1.x. And so here's some more. Constant placeholder. See, now here we've got formulas here. You got Wx is W times x. Y is Wx plus b. That's a line or a hyperplane, right? And there's another way you can do it. You can do it, and you can just do W times x plus b. Boom, one shot. There's a lot of flexibility. And then here's the result. It's vectors, so they're going to be component by component calculations that come out at the end. You can try it later if you want. So now, this is an example of saving the graph. And you can invoke these APIs that are available. And they're, see here we have writer as the summary. That's the syntax. tf.summary file writer. tf underscore logs, just a directory. It creates it if it doesn't exist. Be wherever you want. And then session.graph. So the contents of the graph are stored in a file that TensorFlow creates and puts it in the directory that you specify. And then later, so here we launch it with this syntax, TensorBoard dash, 2 dashes actually, log_dir, and then the directory. Now, another thing, and this is a little minor detail for now, but whenever you have a variable, you have to invoke init. So init is this ugly looking thing here, and then you do a session run init, just the way it works, because you don't have to initialize everything. So it gives you the flexibility to specify either all of them like this or a subset for performance. Okay, so now let me see. I'm going to show you, and before we get to the example, I want to show you, here's eager execution. Requires Python 3.x and supports most of the APIs. At this point, it's going to be the same set pretty much because it's going to replace 1.x. And so here's an example. See the extra import statement, and you see the enable. That's for 1.x. When you do it in TensorFlow 2, you won't need it. It'll be on by default. You can actually specify the old way, the deferred execution, if you want to. That functionality is there. And so what do we do here? X is 2 dot, M is matmul x.x. The result is 4. That's it. No session, no run, no deferred this, that, and the other. So which one do you like better? You don't know? Okay, well, I go for this personally, but right now, most everything out there is going to be 1.x stuff. And Google has over 6,000 repositories as of even a year ago with 1.x. So they're madly, furiously converting all that stuff, which is good, because if they find bugs in the code, then they'll fix it before we have to deal with it. And so when will it come out? Middle of maybe the summer. And 1.x will be supported for at least a year afterward. So no need to panic. Now, the question is, do you learn this now and then switch, or do you wait, or what? Well, I don't have an answer for you. It depends on what you need to do. So it's always that when you get that kind of seismic shift, software changes. And so I would recommend waiting if you can, but at the same time, don't completely ignore it, because when you start working on your TensorFlow 2.0 code and you're going to try to figure out how to do something, well, where are the examples? And you're going to have to probably look at the 1.x examples, but they probably won't help. But if you're going to be working with code that other people have written, and it's the older stuff, there's value in that knowledge. It's not wasted, and it will be relevant probably for some time. So TensorFlow.js, I'm not going to cover because we're probably running out of time. I want to get to some other stuff. It's TensorFlow in your browser. It was called Deep Learning JS, and then it was repurposed, renamed, updated. And so with TensorFlow, and I didn't list this, but you can have stuff on the command line. It will work in something like Jupyter Notebooks. Anyone work with those? Good, you're going to like this, because not only with Jupyter Notebook, but there's something called Google Collaboratory. Who's worked with that? Oh, it's fantastic. It's Jupyter Notebook based in the cloud. And not just that, 12 hours, up to 12 hours of GPU execution time for free every single day. Yeah, so forget about those cards and boards and all that other hardware stuff. If you don't like hardware, this is great. And if you want, you can get a TPU, but that I think is $6 an hour. That price will probably come down at some point. So I'm going to skip over this. And you can look at it online when I put up the slides if you want. And then, okay, so let's just go back to, I want to show you, not that. This is the TensorBoard. See, when I was saying before, so this is the graph. And I mean, it does nothing, this one. But you can do lots of things here. For example, you can't see it, but you can upload stuff, you can save it, resize it, you can just do a bunch of different things. And then when you click on the nodes, you can drill down. There's really nothing in this one, but it gives you the attributes and so forth. So it's kind of component-based. And so you can, like functions, right? You have things that are local. Unfortunately, that functionality about the component-wise stuff, that functionality is going away. And it's okay when it's this size, but if you have hundreds of variables and placeholders and all that, it's going to be quite confusing. So I'm not sure how well that's going to turn out. And so, by the way, it's port number 6006, which is Google upside down without the L, E. Here's Google Collaboratory, and you just search for Google Collaboratory, and you get to the main page. And you only do two things to start. See over here, this connect. I actually connected, so I'll click on connect, and see this is doing its thing. It's connecting to the cloud, initializing something over there. And the other thing that you need to do is very simple. When you go over to edit, click on that. You see the notebook settings? Just click on that. And look what you got. This is the one. The one in the middle. Because when you click on the drop-down, there's the GPU. That's it, GPU enabled. It's 12 hours, up to 12 hours a day per session. And a session means when you're running, and then when you stop, everything you've done goes away. So if you upload data in order to run your notebook and stuff, that goes away. So this session starts counting over. So the reason I mentioned that is because I asked, well, what if I run this 168 hours for the whole week? Do I get 12 hours free for each day? No, you just get the first 12. So just in case they thought about that too. So, and that's really kind of it. And then if you go over to File, I know you won't be able to see this, but there's save as a notebook, save as Python, you can upload, rename, blah, 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 all that stuff. So it's a very, very nice environment, and you get the speed. So in the classes that I have before, even this is a few months ago, well, 4 months ago, we did the CNN stuff and the RNNs, like, well, okay, just take them home and then run it, and then come back with your results in the next session. Now, we can do it in class. So it's a lot more meaningful for everybody. And so now I just want to go to, is it okay for us to have some fun? Yeah, it is, right? We can do what we want. Okay, so there's this, I'm not affiliated with anything I've shown you tonight, including this. This is called deepart.io, and it's a 17 hidden layer convolutional neural network. And what you do is you upload 2 images, and then it does the convolution and it comes out with something. And sometimes it's kind of spooky and a little creepy, but sometimes it's interesting. I mean, it depends on your definition of that. I think this is a little unsettling, I would say, but there's all sorts of stuff. And so it's a free site, I think. So I'm not an artist, so I took my SVG code that was embedded with some JavaScript and HTML pages, launched them, took some screenshots, and my screenshots are the things that I uploaded, the things on the right. Then I quasi-randomly, over a cold one, selected some images online, and then I kind of loaded them up and let it do its thing. So here we have the first one. The thing on the right is, it's what is it called? I think it was a conchoid. I forget. It's a polar equation. I don't remember the name. And who's that person in the middle? Wow. The young'uns know this. I'm impressed. I feel younger now, thank you. So we took the two together, and it kind of, you don't see it very well, but it's kind of okay. The next one is the two cats, that always have the cats. And that was, I think that's okay. This one I like. It seems to have taken sort of like his aura in a way. I don't know. I mean, I don't know what else to call it. Then you can't really see it all that well, but I think he looks more angry in real life than he does over here. This has almost softened him a little bit, kind of. You can check it out online. I think you'll be able to see it. And then this one kind of lame. This is the Picasso, the melted, the clocks, watches, whatever. What did I say? Yeah, what did I say? Oh, jeez. Yeah, sorry. That's right, Dali, it's him. So the thing on the right, I was sort of, again, as a non-artist, I was thinking, take something that's really a lot of jagged stuff, and then the soft, and then morph it, it'll come out something kind of lame. That's okay. This one is interesting because if you can't see it, but the normal eyes are the weirdest part of it all, actually, I think. Kind of, sort of. And then there's Arnold. That one's pretty good, reasonably. This one I like, Lady Gaga. Another more of the aura thing, I guess. So this is all free, and there are other sites around as well. They also do video, so you can record something, except that it's $400 for 4 minutes. Kind of pricey. That was 2 years ago. There's probably other sites out there that you just shop around, and you'll probably find something more affordable. And so, 2 more slides, I think. Where are we here? Just a little bit about, what? Where is this? A little bit about me. Just some of the books I've written. Actually looking for a technical reviewer for the first 2, so if you're able to do so, or if you know somebody, please let me know. I just finished my C programming book. It's going to come out, I think, next month. And there's a mixture of stuff. I don't even remember all what I did, but it's there. And so now what I'm doing is I'm an instructor at UCSC, Santa Clara, Deep Learning TensorFlow. Machine learning class starts on the 18th. Another TensorFlow deep learning class February 2nd. And then later on, all these ETAs are my estimates. Nothing's been finalized there, but those are some of the things that I think there's a decent chance that we'll be offering this sometime this year, middle of the year and later. So it's 10 weeks, 3 hours per session, 30 hours of instruction, usually in the evenings, sometimes on Saturdays. And the machine learning one is 6:30 to 9:30 Friday nights, and the other one in February is Saturdays, 9:30 to 12:30. And so one thing I do like about the Friday night hours is there's kind of a filter, like somebody said. You know that when people show up for that, they've been working all day, they're motivated. So that part's good. And if I was 25, I wouldn't be taking the class. I definitely, not at that night. Anyway, that's basically all I had. I hope this has been useful for you, and thank you for your attention.